Okay, let's go through another example. And we may or may not get to the group fuse lasso. If we don't get to the group fuse lasso, then so be it. You'll probably have a homework problem that introduces you to it. If we don't get to it, we'll make the homework problem a little bit more introductory, so to speak. But it's not going to be critical. It's just a marriage of the group lasso and the fuse lasso. We'll just see if we have time. So let's go through a few examples. Let's suppose we want to fit a very large group lasso. So a motivating example is a sparse additive model, the one we talked about, when D is very large. So I want to fit a sparse additive model to lots of data points in a very large dimension, like thousands. Interior point methods don't make any sense because the iterations are going to be far too costly. First of all, it's going to be a big linear system you're trying to solve. The linear system will be of size, so if I had D dimensions, and let's suppose I chose 10 basis functions per dimension. So I was allowing each dimension to be modeled as a linear combination of 10 sines and cosines, for example, or 10 polynomials or something. Then I have 10D total columns in my X matrix, because I have 10 per dimension. And so I'm going to try to solve a 10D by 10D linear system with an interior point method. And that would be OK if the X matrix was structured. But because we're filling it with just evaluations of basis functions, like polynomials, sines and cosines, et cetera, it's going to be generically dense. Okay, so it's going to be a very big, dense matrix. The interior point method iterations are just too costly. So it's not a good idea to use that in this case. So gradient method is slow, and it's not really much cheaper per iteration than proximal gradient. So there's no real reason to use it. Okay, it's just about as expensive as proximal gradient per iteration, and it's slower. So why would we use it? And so proximal gradient is definitely the way to go in a case like this. And if n is itself huge, then our best bet is probably to use a stochastic version of proximal gradient. Okay, so we talked about stochastic gradient descent. We talked about stochastic subgradient method. We didn't explicitly define stochastic proximal gradient. But here it is. I'm telling you, you just basically take a stochastic approximation to the gradient, and then you apply the original prox. So the prox is always applied to a gradient step in the smooth part. For a stochastic proximal gradient, you apply the prox to a gradient step in the smooth part, where the gradient's been replaced by a stochastic approximation. So for us, the gradient was x transpose times the gradient of h of x beta, because that was just the chain rule applied to taking the gradient of h of x beta. And I can write that as a sum of xi times the gradient in the ith component of h at x beta. Again, that's just saying that I'm here. This is a linear combination of the columns of x transpose. The columns of x transpose are the rows of x. So I've just written it out explicitly as a linear combination of the rows of x, where the weights here are just the components of the gradient. That's all this is saying. And if n is very big, I can approximate this sum by just taking a random sample of the rows and just taking the sum over those rows instead. So that would be my stochastic approximation to the gradient. Take a different random sample of data points over which to evaluate this at each iteration. And then I apply the prox. And the prox, remember, is some kind of block soft thresholding. So it's either given by this one, in which case I'm literally shrinking all of the components by some factor. That's the prox corresponding to the group lasso with the 2 norm, or this one, which is setting things to 0 in a way that's similar to how soft thresholding does. So that was our kind of walkthrough for a very large group lasso problem. Of the methods we've learned so far, it seems like the best thing to do is proximal gradient or stochastic proximal gradient. The flip side is an autoregressive group lasso problem. So I'm thinking about now a case in which, let's suppose we were doing some kind of time series, and I had no predictors. I just had y. Okay, and I was just observing y across time. So I observe y today, tomorrow, next week, etc. And I wanted to model y as a linear combination of past y values. But I thought that actually the behavior could be segregated into groups. So let's suppose I chose delta to be something like 7, and t-index is days. So this is saying like y is some linear combination of the y values from last week, plus some linear combination of the y values from the week before, plus some linear combination of the y values from 2 weeks ago, etc., all the way back to j weeks. Maybe j is 5 or something. This is a typical autoregressive model. I have not done anything specific to the group lasso yet. And if that word autoregressive doesn't mean anything to you, it's just doing a regression of y on its own past values, trying to predict y from its own past values. How we can make the group lasso fit in is we could say, well, I don't think all of the weeks stretching back are relevant. Let's suppose I chose j to be large, like 20. And really only some weeks are relevant, some past weeks are relevant for predicting y. And I want to actually use those weeks in their entirety. I want to pick out like all of week 2. I want to allow all of the y points from week 2 to contribute, and none of week 3, and none of week 4, and none of week 5. So that would be doing the group lasso, where the groups are defined by these blocks of coefficients across week. So I've written out the sum in this form. Okay, so group lasso, where the penalty is just defined by these groups. I penalize all the beta in a particular group. And the loss, we could even just think about doing least squares loss between y and the right-hand side. Just to be doing like a regression. So primal proximal gradient still looks favorable. It's still not a bad idea here. Nothing's changed. We've just basically all we've done is we've said the X matrix is this particular matrix. Okay, the X matrix is a particular matrix that's defined by filling in past values of y. But now interior point methods actually look better. They look like a lot more favorable because this X matrix is banded. So let's draw the X matrix so that you can get a sense for what it looks like. So my model here is saying that y, say y1, let's just do groups of 2. Okay, so y11, let's say, I'm saying is approximately equal to beta 1 y10 plus beta 2 y9. That's my, say, my first group, plus beta 3 y8 plus beta 4 y7. That's my second group. All the way down through, this should be beta 9 y2 plus beta 10 y1. That's what, for example, the model would look like if we had groups of size 2 and I was just looking at time point 11. I can think of this as actually just a, right, I can fill, let me just call this guy x1 and this guy x2. This just looks like this, right? I'll call it x11 since I'm at 11th time point, comma 1. This is just a linear combination of some predictors, those predictors being past y points. That's all I'm doing. I'm just translating this into more familiar notation. So beta 9 times x11, 9, plus beta 10 times x11, 10. Okay, I've just translated this autoregressive model into like a notation involving some predictors x. And now if we were to set up, for example, if we were to think about the x that would be required, so that I've just specified x, and this is the x matrix in row 11. You can see that I've just specified the columns of x matrix in row 11. But if I were to continue on in this fashion for all the different rows, you see that actually this matrix that I end up defining is going to look banded. Because Is that true, actually? I'm seeing if that's... I'm actually not sure that it's banded now that I've written it out like this. I think it's just that it doesn't have very many columns. So it would be banded if we took beta to be quite large and we restricted yeah, okay, so you're going to have to forget this last paragraph. I was trying to come up with an example where the interior point methods would look good. They're going to look good when this matrix X is this matrix X that appears in the Hessian is banded, for example, right? Because then I can solve this linear system quickly. So I wrote down an autoregressive model, but now that I've written out what it looks like for you, it doesn't result in a banded matrix. It's just a matrix where the number of columns isn't very large. So, okay, that might make this a good idea just because X transpose X is not going to be a very big dimension, but it'll still be dense. So forget about this last paragraph. Maybe actually this example of an autoregressive model is an interesting one to apply the group lasso in, but interior point methods don't really look any better than proximal gradients, say. So I'm just going to introduce for you what group fused lasso problems are, and then I'm going to go to the punchline for these two lectures on case studies. So the group fused lasso is a marriage of group lasso and fused lasso in the sense that we are taking now differences across groups of variables. So it has the difference aspect of the fused lasso, and it has the group aspect of the group lasso. And again, we can think about splitting up our variable of interest beta into blocks or into groups. And the penalty now is between differences of groups rather than just on groups themselves, as we saw with the group lasso. So as with the fused lasso, common choices are for the graph it's like a chain, which means that I'm just looking at the difference between beta I and beta I plus 1, neighboring groups in that sense, or a grid, or a fully connected graph. And as with the group lasso, the common norm choices are just 2 or infinity, because that's going to be setting differences to be 0 exactly between some groups. So this is a nice example. We'll just go through this one example real quickly from a paper that Matt wrote with his advisor. So in this example, there's a model for human motion, and different motions are being performed across time. So for some increment of time, the amount of time being unknown, suppose some model is performing jumping jacks, and then it starts jogging, and then it starts squatting, then it starts doing something else, and starts doing something else. And Matt, you can cut me off if I'm not explaining this properly, but as I understand it, the goal is to take a bunch of sensor readings, which are connected to various parts of this this individual, simulated individual, and to be able to fit a dynamical model for motion, but where I'm allowing the coefficients to all of a sudden all change across time as I enter from the jumping jack phase into the jogging phase. So for example, what's being shown here is the data, and there's some linear model for jumping jacks in this phase, and those coefficients are being estimated. They're not being shown. But then as soon as the individual starts jogging, all the coefficients are allowed to change, because the dynamical model for jogging is just a different model for what it is for jumping jacks. And so if I'm placing a difference between the coefficients for jumping jacks and the coefficients for jogging across time, then they're going to be all the same, basically through this region, and then they're going to be all different. So they're going to stay the same across time, and then every coefficient is allowed to change at some point once the individual enters the jogging phase. But the point is that we don't exactly know the lengths of time for which these actions are performed. So the group fused lasso is helping us out by determining where these fusions are going to occur. So shown here are the differences in coefficients across time. And where it's non-zero is where the model has determined that there's a change in the motion. And you can see they roughly line up, right, with these gray vertical bars, which are placed with knowledge of the truth between where the transition points occur between these motions. Okay, so it does a pretty good job of picking up when the dynamical system changes. So that was an example of the group fuse lasso. The algorithms, they're all harder. Let's just leave it at that. They're all harder. Nothing is very easy. That was maybe a fair summary. Everything is hard. So to solve it, we're going to resort to something else, which is something we're going to learn next time, which is operator splitting. I mean, you can solve it without operator splitting. You can solve it trying interior point methods or trying stuff like proximal gradient, etc. on the dual. But none of it works as well as it did for the fuse lasso or for the group lasso. It's just a harder problem, as you can imagine. And we'll use this to motivate something we'll learn real soon, which is called operator splitting. It's a very, very flexible platform for doing optimization. And it can handle the group fuse lasso. It can handle fairly sophisticated problems like this one, where we have sophisticated compositions of norms and linear operators. Okay, let me get to the punchline. What did we learn from the case studies? There's a bunch of points that we learned, and then I want to talk very briefly about some implementation issues. So here's what we learned. There is no single best method. Performance really depends on the structure of the penalty, the conjugate of the loss function if we're taking the dual, the desired accuracy level if you want a very accurate solution or just a rough solution. We even saw that it depends on the value of lambda, the regularization parameter. Sometimes if lambda is small, that's helpful for dual methods, and if lambda is big, it's helpful for primal methods in this case. We learned that duality is, kind of always a good thing to look out for. So there's no real downside to deriving the dual aside from it would take you a bit of time. And the dual often offers a complementary kind of structure to what you see in the primal. Okay, so for the fuse lasso, we saw it was actually really quite useful to derive the dual. We saw that regressors, or an X matrix, it complicates the duality relationship in general. So that's pretty much always true. Okay, it's because once we have a function composed of a linear function, its conjugate is just more complicated, and it involves something like the inverse of X transpose X or something of that sort. So with regressors or predictor variables, whatever you want to call them, the duality relationship becomes more complicated. It's kind of unfortunate. But you can use proximal gradient on the primal to reduce your primal problem to one without predictors, essentially. Right? Because in that case, you've approximated the loss by a quadratic that doesn't have any X matrix in it. And the last two things we went over rather quickly, but it helps to recognize easy subproblems. We saw this last time with Matt, where there was a subproblem that we recognized we could solve with dynamic programming that was quite efficient, and so we could design an algorithm around that. This is a good general principle. Think about if you didn't have these constraints, if you didn't have this part, does the problem get easier? If you can recognize an easy subproblem, then you can often design an algorithm around it. You maybe want to start thinking about how you can utilize that fast hammer you have for a subproblem. And this one we really didn't talk about much, but this would be something you might cover if you take, sometimes we offer an advanced course on optimization every 2 years. Sometimes this is covered in Williams' big data class for machine learning. At scale, memory is really an issue, so stochastic methods are really a good idea, and they may be your only option. Okay, so doing things that have cheap iterations that don't converge very quickly, but that use some kind of stochastic trick really are maybe the only option for very large problems, and they look much more favorable there than they do for regular sized problems, where we typically just laugh at them because they converge so slowly. So those were the general principles. I actually don't have time to go through the implementation tips, so maybe we'll start with that next time. But I'll just say, before we start this advanced unit, your toolbox is only going to get bigger. So we're going to learn between now and the time the course is over something called the alternating direction method of multipliers, which is an operator splitting method. We're going to talk about coordinate descent methods, projective Newton methods, path following methods. And you're going to have only more algorithms to solve these problems. And in fact, for the problems we saw, for most of them, we might want to use something like coordinate descent or operator splitting in favor of what we already saw. So these are very good algorithms that are very widely applicable. And something to keep in mind is that you don't have to always design the perfect optimization algorithm. It's not like you're trying to, have the very best algorithm and that you somehow feel ashamed if you missed coordinate descent in favor of 8mm. You just have to find the one that works well for your problem. Okay, there's the notion of optimality and optimization, I think, is not the same as it is, say, in data analysis or machine learning and statistics. You just have to find the right algorithm for the job. It doesn't have to be the perfect one. So you should be going through the motions of thinking about what we did in these last 2 lectures. What are the strengths and weaknesses of the various approaches? But settling on something that works well that you can implement in a reasonable amount of time, that's the goal, right? Not finding the one algorithm in the literature from 1982 that is like perfect, that no one else has thought of. That's maybe not the goal most of the time when applying optimization routines. Okay, I will see you guys next time. We'll talk about a bit about implementation and then on to 8mm.